Hi everyone, my name is Tao Yang. I'm from University of Utah. Today I will present a paper, Maximizing Marginal Fairness for Dynamic Learning to Rank. It's a joint work with Professor Qingyao Ai. Rankings are ubiquitous. We can see a ranked list when we shop online. We can see a ranked list when we want some results from the search engine. We can see a ranked list when we want to go some nearby restaurants. We can also see a ranked list from when we want to see a movie online. But how to rank them is what we are going to discuss today. Let me first give you a motivating example. For example, here we have two companies, company 1 and company 2. Each company has 3 movies. Company 1 has ABC, movie ABC. The number here indicates its relevance. How likely a user will like this movie. When we want to do a ranking task, we are going to rank them. Traditionally, we will sort the movies according to their relevance. First we rank A, B, C, then D, E, F. However, each rank has its exposure. Here we exposure is defined as how likely a person or user will view this rank, and we accumulate the relevance and exposure for each company, and we found that although the movies from each company are very similar, got very similar relevance, however, their exposure are tremendously different. The reason is that there exists a large scale of exposure between top ranks and bottom ranks. That's the reason is that we human beings are always put much emphasis on top ranks instead of the bottom ranks. How to mitigate the difference between relevance and exposure? Previous researcher proposed that we need amortized fairness, which means relevance helps to decide the exposure items should get. The exposure should be proportional to the average relevance, and the more the more relevant an item is, and the more exposure an item should get. It makes sense. But is this proportional relationship enough for ranking? For example, we have 8 movies, and we assume that it satisfies the proportional relationships, and it's fair. However, when we only take a look at the top 4, results can be severely unfair. And in this paper, we propose fairness in top K settings. Since we want to evaluate how unfair rankings are at different prefix, just like NDCG, we think the top K fairness are more important. Based on the top K fairness, we proposed the marginal fairness, which is the marginal gain of fairness when we introduce additional document. And when we iteratively select items with maximal marginal fairness, it can help to mitigate unfairness. In this paper, we proposed an algorithm, MMF, which introduce a stochastical mechanism to select items between the one with maximum marginal fairness and the one with the largest relevance. The greater lambda is, the fairer the rankings are. Of course, we did some experiments to evaluate our method. There are two data sets. One is the news data sets with simulated preference. There are 30 articles from two groups, left-leaning and right-leaning. And we also pre-processing movie lens datasets to get 100 movies from 5 companies. In this paper, we simulate clicks and infer relevance from the clicks by using some unbiased learning to rank clicks, techniques. And here are 6 methods we are going to compare. The very first one is the naive algorithm, which rank items according to clicks. Since it's not ranking according to relevance, so it's a biased algorithm. We also use unbiased estimator or to estimate relevance and then do a ranking. So the remaining algorithms are all unbiased algorithms. And the first 2 are unfair algorithms, since they only consider relevance. And the last 3 methods we are going to compare are fair methods, which will try to trade off between fairness and relevance. Let's first take a look at this graph. We want to know whether the unbiased estimator is truly effective, even when we mitigate unfairness at the same time. Fortunately, yes, it's truly effective. As you can see, what the unbiased algorithm can, let's take a look at this graph. The horizontal is how many presentations, how many users have seen the data sets, and the vertical are the difference between of relevance between estimated relevance and ground truth relevance. As you can see, the unbiased algorithm can converge to 0. I mean, the difference between the relevance difference can converge to 0. Thus, we can make a conclusion that the unbiased estimator is effective. While the naive algorithm, which is the unbiased algorithm, it has a difference which can't be which it has a difference. There always exists some difference between the relevance used in naive algorithm. Now let's take a look at how our method can perform in terms of trade-off between fairness and relevance. As you can see, our method MMF, the black line, can achieve better NDCG performance compared with other fair methods like linear programming and FairCode, while it has much lower unfairness. So we can claim that our method can achieve better trade-off. And such performance also exists in movie lens datasets. Here is a table that summarizes the performance of this paper. As you can see, our method can achieve better performance at top ranks at NDCG and unfairness. However, we also found that our method compromise a little bit of long list fairness, while the state-of-art methods, Fiocco and linear programming, are good at. Thus, we would know that existing state-of-the-art methods are only considering long list fairness, which ignores the top K performance. That's the contribution we make in this paper. And we have made 3 contributions in this paper. We propose a concept of marginal fairness, and we develop a metric to measure the fairness in top K results. And we propose an algorithm to trade off the relevance and fairness. That's all. Thanks. Are there any questions?